So today I'll be talking to you about Gribby. It is an open interface for programming your RIB. There's been no shortage of mechanisms for interacting with your routing information base, routing protocols, not the least amongst them. But what we've had is a paucity of mechanisms that are consistent and open. So a little bit about the why for doing something along these lines, talk about a couple of use cases briefly, dig into the details of Gribby, and then just kind of walk you through a sample interaction. So why? Why would I want to inject something into my routing information base that's not learned from BGP? And how would I go about doing that? So we have IGPs for exchanging reachability information. How do I know how to get to various locations inside of my AS? We have BGP for exchanging routes, more broadly, or for exchanging routing information within our AS. But sometimes we want to do something surgical, or we want to be able to divert traffic within our domain or to another domain. And the tools for doing that are like all over the map. And I'll talk briefly about three techniques that are pretty common out there. One is direct programming of forwarding entries into the hardware. This is using techniques such, protocols such as OpenFlow or P4 runtime. We have been doing this with technologies like BGPLU or BGP SRTE to use routing protocols to do kind of surgical traffic engineering. And then we have kind of vendor-specific device APIs or SDKs that allow folks to write agents or to interact directly with the routing daemons in the particular network operating system. I would be remiss if I didn't give some credit to the folks at the IETF and the I2RS working group. They did go through and standardize or attempt to standardize some of the items I'll be talking about here today. Traction on this, frankly, has been weak, and I don't really know of any I2RS implementations out there that folks are actively using. So why not do direct programming of the device? Why wouldn't I just use OpenFlow in order to program something directly into the device in order to provide this? Well, a couple of things. That requires that you have a controller or something, and I should kind of pause and say, hey, all of these require that you have a controller or some entity off box that is injecting information into your RIB or into your FIB. But these protocols require that you have a very low-level understanding of what's going on inside of the device. If you're working with OpenFlow or P4 runtime, you're actually have awareness of what the hardware forwarding tables look like, and you have to go through and do a lot of the heavy lifting associated with generating the next hops and programming them into the hardware. So they don't play nicely with existing routing protocols that you're probably using in your network today. You have to kind of build the whole thing yourself. To that point, the controller has to know how to resolve routes, and typically that is some sort of shimmed interface to the IGP. It is able to resolve that, and then it programs the actual hardware entries using OpenFlow or P4 runtime. This is not for the faint of heart. This is a pretty complex mechanism to go about doing it. If you are going to do this, you really need to know exactly what you're doing. Why not use a routing protocol? We have BGP SRTE, we have BGPLU, we have PSEP, we have kind of additional bolt-ons to existing routing protocols in order to kind of do this surgical routing. Unfortunately, we find ourselves force-fitting a number of interactions when we go about doing this. BGP SRTE is still somewhat commingled with the BGP decision process. You don't necessarily, it's a very complex decision process. And then, we don't get some of the fine-grained behaviors that we might be really interested in terms of, like, did I actually get what I asked the device to do? And so, like, what we'd need to do is we'd need to impose our will on the system using whatever the routing protocol of choice is. Then we'd have to read out the system state to be able to validate that, yes, what I asked the device to do is what I got. And the mechanisms for getting that are pretty, they're all over the map. There's no real standardized mechanism for doing that. although that's been updated recently, and it's actually at the core of what we're doing with Gribby. And then there's no acknowledgement. I don't get an acknowledgement that the device did something. Programming, we can have an intelligent response from an RPC. If I'm doing this with routing protocols, I basically send my intent to the device, and I cross my fingers and hope that the device did what I want it to do. Which brings me to the last kind of common mechanism of doing this, which is to use a vendor SDK. So I work at Arista. We have EOS SDK. We've worked with a ton of our clients, customers to let them build and extend EOS in ways that are unnatural to others but natural to them. And the nice thing here is you can do exactly what you want with the software, but it's not particularly portable. I can't take what I write for Arista and apply it on Junos. I can't take what I do on Junos and apply it on Arista or Cisco. But if you're a single vendor shop, like this may be a viable means of being able to interact with the RIB in your system. But the punchline there is it's not open and it's not portable. Which brings me to Gribby. Gribby, the G is for gRPC, the RIB is for routing information base, and I is for interface. And this is a gRPC service that allows us to effectively do three things. One, we can program routes, we can create logical forwarding structures inside of the system, and we can interrogate the device to see, like, did you do what I asked you to do? From the switch or router's perspective, this is just another control plane service. It manifests itself largely like another routing protocol. This is, so like I mentioned earlier, it manifests itself just as another routing protocol. Some implementations have this as a routing protocol that has a different administrative distance, so you can control the ordering of the route programming. I would like to point out here that this is not configuration. We're not pushing static routes or anything along these lines into the device's persistent configuration. We're really just programming RIB entries. So how do we do this? Well, first off, we need a data model. And so what we're using here is the OpenConfig abstract forwarding table. Now, each vendor has their own notion of what the forwarding table looks like. And that forwarding table representation is going to be subject largely to the whims, nature, and implementation details of that particular forwarding platform. The AFT is an abstract representation of the forwarding table. It is not complete in terms of all of the behaviors that a vendor fib might represent, but it's typically more than good enough to get the job done for doing traffic engineering or for doing routing overlay. There's a couple of things that are not represented in the state model here. Obviously, we have, I'm just representing a portion of the model here. IPv4 unicast entries, we have a prefix. You'll note there is no configuration component to this model. It is all state. And then we have decapsulation headers. We have next hop groups, so we can have some notion of UCMP. And we can have network instances, which are the OpenConfig or AFT notion of VRFs. So we can program VRFs. We can program ECMP groups or UCMP groups. What's not represented here is the ability to also tag a weight associated with a next hop inside of a next hop group. And what is hinted at but not explicitly stated in my depiction of the model here is the ability to have multiple types of forwarding instances. And by that I mean multiple tunnel types. So I can have IP and IP tunnels, I can have MPLS tunnels, I can have IP over GRE tunnels, I can have MPLS over GUI tunnels. These can be represented inside of the RIB, and it's simply a function of creating the logical tunnel type and associating routes with it. I should point out that these are all open models. The community at large has been contributing to OpenConfig, and I'll kind of gloss over some of the nuances that are lost in representing this as an abstract instance, but effectively what we're going to do with Gribby here is we'll use this notion of an abstract forwarding table to be able to modify the RIB directly. And one of the nice things that we get here is we now have a stable, open interface to interact with the RIB in a transactional manner. So each request that we make to the Gribby server running on a router has a unique ID. So we can correlate what's going on from a client over here, which is pushing routes into the router from a controller or some other station with what's actually going on in the device. The other thing that we get here with Gribby is we get some notion of a fib programming ACK. And there's actually two levels of ACKs that we get. And we can get a kind of a top-level RIB ACK. Did you program this in the RIB? And we can even go deeper, and we can say, did this ACK make it into hardware? This isn't perfect, but it does let us kind of bypass this need to have a closed loop of telemetry and RIB programming. So we can have the device, when we send it a modify request, send us back with a get, yes, I did this, and here's the response that's associated with it. If there's a failure, the controller can actually do something meaningful with it and take immediate remediative action. A couple of other niceties in the interests of HA, we have support for redundant clients. I can have active standby, active. We have a notion of programmed entry persistence. So if the Gribby agent or process running on your router should die, it doesn't necessarily mean that the entries are gone. They're still persistent in most vendors' RIB implementations, so that the Gribby daemon can restart and you're back to where you went. You will have to do some resynchronization with the controller in order to make sure that you're both on the same page as to what the state of the system is. And the other thing here is we're using gRPC, and love it or leave it, it's a pretty popular RPC protocol. It's open, it has support for a wide variety of languages, Ruby, Python, Go, C++, you name it, it's out there. We can also lather up the connections with encryption by using MTLS, so we can do things like provide roles and capabilities on the box that allow us to say, this user is allowed to do these actions, this user is not allowed to do these actions. So I'll talk a little bit about some of the use cases where folks might want to be able to do this. There's kind of three scenarios that kind of run into persistently here with the customers that I work with. They want the ability to inject prefixes into a VRF for scrubbing, for doing something with DDoS. Gribby route, as I mentioned previously, is just another route with its own type and preference. You can have the routes resolved within the context of a particular network instance or VRF. Another example here is you can manipulate label stacks with Gribby, so you get the benefits of MPLS traffic engineering, and you can actually create UCMP sets here that allow you to load your network for traffic engineering based on your available capacity. And then tunnels seem to be the source routing mechanism of choice, and everybody has their own tunnel mechanism. So we can actually dynamically bring up tunnels, associate next hops with them, associate routes with them, and tunnel traffic over the infrastructure without making any changes to the base IGP cost associated with the network or doing anything novel with what is fundamentally just reachability information. Again, this is route injection. This is not configuration, so we're not going in on the CLI and saying, give me interface tunnel 100, NCAP, GRE, destination, source, all of that. We are programming these entries dynamically into the RIB. So digging into the DDoS scrubbing scenario a bit further here, what we have is a router here that wants to divert the traffic through a scrubber. I have a tunnel destination here, that's sourced at the all ones to the all twos. The traffic is destined for 100.1. What we do here is working our way kind of from the lower right-hand corner here. We see the construction of an IP-IP tunnel. with a source of all ones, a destination of all twos. This is given a next hop entry of 100. On top of that, I can say that this is the next hop group that is associated with this. It's a single next hop group that has a given weight of all of the traffic associated with this next hop. And then moving to the top here, I can associate a surgical /32 route with this particular next hop group, cutting through all of the standard IP routing semantics that are programmed into the device as a function of the routing protocols. If I kind of shift gears here to the MPLS domain, I can create label stacks. So in the lower right hand here, I have just the one label stack here, which is inner 201, outer 300. I'll skip through the definition of all of the weighted or UCMP legs here that are provisioned. I can assign weights to them. You'll note that the next hops in this portion of the, in this portion of the configuration are not equal. And then I associate a top-level label here, or a BSID, with this particular forwarding entry. So what I get is the benefits of BGP SRTE with an actual ACK. I know what the system did here. I know what the system was programmed to do. I'm not using an alien protocol in order to do this. And I don't have to worry about the interactions with the BGP SRTE decision process. Moving on here, I'll talk a little bit about the RPCs themselves. As I mentioned earlier, the AFT model is effectively state only. So it's taking in all of the various sources of routing information in the system. It's rendering a fib. So as such, the Gribby RPC here is just a modify. And a modify has a couple of parameters associated with it. A modify request operation has the ID that I mentioned earlier. It indicates the VRF, or network instance, that it's taking place against, and then the operation that I'm interacting with here, which is the add, replace, a delete operation, and a corresponding entry, which is the definition that we provided previously. The server on the router will respond with the ID, and then the RIB or FIB ACK status, and a timestamp. So I get some ability to actually go through and trace what's going on here. A little bit about the session parameters. These are how we control the active standby nature of the controller interactions. This is also how we define how we want things to be persisted when we are programming the device, and also how we specify the ACK types that we're seeking with this with a given RPC instance. In the interest of ensuring that you only have one controller providing entries into the RIB at a time, there is a notion of an election ID. When a client connects, it sends its election ID. The device tells it what's the highest election ID I know about, and then the server only processes the operations from the connection with the highest election ID. I mentioned earlier there's the ability to get the state out of the device selectively here. So what we have is a GET request. So you can interrogate the device to give you information about all of the routes associated with a particular VRF or AFT type. And then it will stream back the entries that it knows about in that RIB or for that particular portion of the AFT with the last known state of the acknowledgement for that particular action. And then finally, the flush interaction here. This is, when all else goes wrong, you can flush the device's knowledge of Gribby routes. And this can be used to, if your controller goes sideways, basically pull out all traffic engineering information associated with the Gribby route sources and revert to what would be kind of least cost, the shortest path first forwarding. I'll just step through a quick example here that shows how we can do UCMP with simple route entries. So starting from the left here, we have the connection parameters. We're going to preserve the persistence. This is a simple connection. It's only a single controller with one election ID. We're going to add. We basically work our way up in terms of the abstractions. So at the lowest level here, what we're going to do is we're going to specify a next hop, which has an IP address of 192.168.1.1. I should probably set this up a bit. In the upper right-hand corner here, I have traffic incoming to the device with a destination of all ones. I want to resolve that over the next hop associated with 192.168.1.1. I'm injecting a static across all of these interfaces in order to provide ECMP for this, but what I really want to do is I only want to use some of these interfaces for resolving the 111 traffic, and then I also have in the background, and we'll see later here, kind of 222 traffic, which is resolved similarly. But in this case, what I want to do here is I want to build the next hops here. So I'm going to specify Ethernet interfaces 2 and 5 as being the next hops associated with this particular route. I'm going to assign weights to them. So I've got the next hops built here, indexes 3 and 4. I will assign weights to them. You'll note that the weights are not equal. And then I will associate a route with these. So what I'm doing here is now I'm just pointing 111/32 to resolve over the next hop group that is constructed here using those interfaces. When I read this out from the device, you can go back here and see the weights here of 1 and 3. I've programmed this against the default VRF, and now I have selective weighting. I have 75% of the traffic going out Ethernet 2. I have 25% of the traffic going out Ethernet 5, and you can see down below here these are the next hops that have been configured in order to resolve 192.168 out those respective interfaces in order to provide standard UCMP. So in conclusion, I think what we've had over the past couple of years, particularly with OpenConfig and the kind of first multi-vendor implementation of an abstract RIB and FIB that folks can interact with, is an opportunity for the a first kind of open programming interface for the RIB. We can do pretty much anything that we want from a next hop construction perspective here. We can create tunnels, we can do surgical routing with the existing underlay, we can populate VRFs with this, and we're not constrained to like bespoke protocols which are developed for traffic engineering or overloading things like BGP in order to do kind of unnatural acts. And so I would point out, like, while I do work for Arista, there are implementations from Juniper, there are implementations from Cisco. I'm sure there's a Nokia implementation out there as well. Multiple implementations of this do exist. It is a far more developer-friendly mechanism for folks to interact with the routers. It is something that can be leveraged across a wide variety of network operating systems. And we're now at a point where, as an industry, we don't have to necessarily do one thing with PCEP, one thing with BGP. We can actually start to unify how we interact with the devices in a fairly cohesive and common manner. With that, I'll open it to questions. If there are no questions, I'll just follow up. There are a handful of references, GitHub repos, a motivation document, a bit of specification, a couple of implementations are out there already in the wild. Thank you.